Before I get started on the talk, I just want to acknowledge all the collaborators who contributed to this work. So, in addition to Antoine, I've boxed in this red box the young people who have really driven this work forward. So, it was initially started by a student of mine, Jeremy Lehan, and then current and former CCQ postdocs, Harry Labolita, Fabian Kugler, and Jenny Coulter have really been instrumental in kind of taking this work to the next level. So what I'll be talking about in this talk is DC conductivity and DC resistivity, and of course we all know that this property is important for materials for applications, but also it's really one of the most fundamental defining probes of electronic phases. So if you remember back to your undergrad solid state physics, you probably learned that an insulator is defined as a material where the resistivity increases exponentially as we go down in temperature, whereas a metal has a finite resistivity and that increases like a power law with temperature. And of course, a superconductor is often defined as a material whose resistivity drops to zero. So resistivity is definitely a kind of a fundamental property of materials of condensed matter systems. But there's what I'd like to show in this talk is that there's still kind of a lot of surprises and things that maybe we don't understand as well as we should in terms of DC resistivity. And so I like this quote that Antoine had pointed out to me at some point by Nevin Barsic, which is when exploring the properties of material, resistivity is the quantity that is often first measured but last understood. So this talk will be about metals, and I'll just kind of remind you quickly what the canonical picture of the resistivity of metals looks like. So in metals, we go a step further and we interpret the different power law regimes as indicating different dominant scattering mechanisms. At low temperature, we have this temperature-independent residual resistivity coming from disorder and impurities. Then we have an electron-electron part at low temperature that will be T squared if we have a Fermi-Liquid. And then at higher temperatures, usually we assume that electron-phonons take over, and electron-phonon scattering in the so-called Bloch-Gruneisen picture, we have a T to the fifth scaling of the resistivity that turns into a T-linear scaling of the resistivity. And we can see this all nicely if we put the resistivity on a log-log plot. So there's been a lot of work in this community on this electron-electron part of the resistivity because, of course, in strongly correlated materials, this can dominate over the electron-phonon. So as Antoine said, I kind of come from a more conventional electronic structure background, and there really the electron-phonon part has been the dominant area of improvements in techniques and calculations of materials and things like that. And the reason that that's been the case is this electron-electron regime in kind of what I would call normal metals is actually very difficult to actually see experimentally. So by normal metals, I mean metals with relatively high conductivity and therefore kind of relatively moderate to low electron correlations. And so here's an example of a bunch of measurements done on copper, and you can very clearly see the Bloch-Gruneisen electron-phonon behavior, T to the fifth turning into T linear. But it's very hard to resolve any kind of Fermi-Liquid T squared regime at low temperatures because of kind of the complications from residual resistivity and from the dominance of phonons. So there have been some materials some normal metals where this Fermi-Liquid T squared has been measured. Some transition or noble metals like palladium, I think, is the key example. They show T squared, but that has been attributed to scattering between bands of different masses, not the Umklapp Fermi-Liquid scattering that we usually consider. Probably the most canonical examples are the alkali metals, where a very robust T squared has been measured at low temperatures, but actually there's still some questions in terms of the comparison between experiment and theory and the understanding of what's going on here. So basically, I would argue that this Fermi-Liquid regime in kind of normal metals is really an unsolved problem experimentally, and therefore worth tackling theoretically. So, of course, you might ask, well, if you can't even observe this regime, why would we study it theoretically? And I give three main reasons why we're interested. One reason is that these materials give a really stringent test of our computational methodology. So because of the very low magnitude of the scattering rates in high conductivity materials, it requires very fine convergence of numerical parameters to get accurate results. Also, these are materials where we would assume at least that there isn't any kind of exotic physics going on. And so they can really serve as a test bed to test the formal transport theory that we use in real materials. And so the testing the assumptions that we sometimes make about a local self-energy and neglecting vertex corrections, separating electron-electron from electron-phonon, etc. You might hope that it can be done more cleanly than in materials that have kind of exotic physics going on. And then the main motivation and kind of what will serve as the basis of this talk is that there are some, I will say, kind of mysterious cases. And those are cases where a T squared scaling of the resistivity is observed, but Fermi-Liquid electron-electron scattering is not really expected in the regime that it's observed. So I'll show an example of this, and this will be kind of the topic or the through line of the talk. It's in two very simple materials that I think are probably known to many of you. They're perovskite oxides, strontium vanadate and strontium molybdate, both cubic, at least at high temperatures. So they're quite simple materials. And the interesting thing is that if you plot the resistivity versus T squared, you see basically straight lines. So these are a bunch of collected experimental data. And so these materials show a T squared scaling of the resistivity up to very high temperatures, including room temperature. And so there's a lot to unpack here with the experimental agreement and disagreement that I won't go into too many details. But I just to say that these materials show these T squared behavior, and I definitely wouldn't consider these strongly correlated materials. In fact, there are some of the highest conductivity metals that are known. Here I'm plotting room temperature resistivity for basically the highest conductivity metals measured. And you can see especially strontium molybdate is very high conductivity, similar to alkali metals, lower even than some elemental transition metals. And strontium vanadate also has a quite reasonable room temperature resistivity. So these are materials which are not strongly correlated, but they show this T squared up to high temperatures where we'd really expect them to act like normal metals that mostly show electron-phonon driven resistivity. So what is going on? So do we get this T squared scaling? Why don't we see what we would normally expect from electron-phonon? So that's kind of the motivation, and what I'll be talking about in this talk is basically how we use DMFT plus DFT to address this question, extract electron-electron scattering rates, and especially some of the aspects that we've been working on to try to make sure that we are free of numerical noise in these calculations. Then I'll put this in the context of these two materials. And then finally, I'll talk a little bit about the role of phonons and electron-phonon coupling in the T-squared behavior. Okay, so I know there's many experts in the audience, but just in case there are people who haven't thought about transport using DFT plus DMFT in a while, our starting point is the Kubo formula. We, again, as usual, assume that we have a local self-energy that we obtain from DMFT, and thus we can neglect vertex corrections. And then from a DFT calculation, we extract band dispersions with which we get band velocities and band energies to construct this current correlator and the spectral function. So we have here, of course, a derivative of the Fermi energy with respect to temperature. And so if we're interested in the low temperature transport, then basically this focuses us in around a very small region around the Fermi level. So we could define a scattering rate as actually the imaginary part of the self-energy just evaluated at exactly frequency is equal to 0. Or if we're in on imaginary frequency, extrapolated to imaginary frequency equals 0. And then in the Fermi-Liquid regime, we should see that the scattering rate has a quadratic dependence with temperature. But of course, as many of you know, obtaining low energy properties of the self-energy to high accuracy is very challenging. And the reason is, well, there are several reasons for this. One reason is that we're usually doing our calculations on the Matsubara axis, and therefore, depending on the temperature at which we do the calculation, we have some low energy regime where we have no data points. We have a lowest Matsubara frequency, and below that we have no data points, and so we need to do this extrapolation to 0 frequency. And even if we do analytic continuation, where we can just evaluate the self-energy at 0 frequency, 0 real frequency, what I'll argue and I'll show later is that in this low energy regime, we are analytically continuing from a Matsubara self-energy that in that regime has no points. So in some sense, we are also extrapolating when we take this value of 0 frequency self-energy. So what we have found to be very useful is to really take advantage of the scaling of the known scaling of the self-energy in the Fermi-Liquid regime. And so it has this interesting scaling, as many of you know very well, where the low order frequency and temperature scaling has the same coefficient. And you can actually rewrite in a very compact form the coefficient of the T-squared resistivity with respect to this coefficient of either the frequency and the temperature scaling. And the only part here that comes from the DFT calculation is the so-called transport function evaluated at the Fermi level. You can think of this as the Drude weight. So basically, what we can boil down the problem of calculating the resistivity in the Fermi-Liquid regime, at least, is to calculating this coefficient C. And therefore, we can get away from just looking at the 0 frequency part of or point of the self-energy, and we can fit the full frequency dependence. And as I'll show, that gives us a much more robust calculation of C and therefore the resistivity. And specifically, if we make this plot of imaginary m sigma versus over pi squared t squared versus omega over t, then the scaling relation basically means that all the calculations at different temperatures should collapse to the same curve. And we can also do this on the Matsubara axis, as I'll show in a few slides. So that was just a couple of words about how we extract the electron-electron scattering. Again, I apologize to any of the experts in the audience. Now I'll put it in concrete terms in the context of these two materials, strontium vanadate and strontium molybdate. So first, I'll just kind of flash the computational details of the calculation. So the DFT is done with FASP. One key thing is that we do 1A interpolation and then adaptive Brillouin zone integration using the AutoBZ code, which was developed here at CCQ. And then for DMFT, tricks and solid DMFT. And then one of the key things that we found very useful to kind of gain confidence in our solutions to the impurity problem is comparing these two distinct solvers for the problem at hand. So the first is just the continuous time quantum Monte Carlo solver, hybridization expansion, which of course is on the Matsubar frequency axis. And then we use Pade analytic continuation to go to real frequencies. And then we compare that to numerical renormalization group, which is directly on the real frequency axis. Okay, so that was kind of just a very brief run through of the computational details. So the electronic structure of these materials, I think, will also be very familiar to many of you. They are materials with T2G d orbitals around the Fermi level. Actually, in these materials, this orbital manifold is pretty well separated, so we can treat that as our effective model for the DMFT. And so here are some calculations of the self energies on the Matsubar frequency axis, and then the Pade analytic continuation to real frequency. And we can see that in both cases, at least at low frequencies, the continuous time QMC and the NRG agree very well with each other. And I'm kind of brushing over a lot of kind of computational details and headaches that made this possible. But this gives us confidence again in not only the solution to the impurity problem, but also in the analytic continuation at low frequencies. Though I'll show that actually this agreement is not enough to get converged scattering rates. So we also see this Fermi-Liquid-like omega squared dependence of the real frequency self-energy. And so at the temperature of this calculation, which is 116 degrees Kelvin, we could say that these materials are in the Fermi-Liquid regime. Of course, we can do better than just fitting a parabola to the low frequency behavior. Just to contrast a material that I'll show a little bit later, the non-Fermi-Liquid strontium ruthenate has quite a different behavior and notably a much larger scattering rate at zero frequency. So I'll come back to that in a second. But as I was saying, we can also, we have many other ways of diagnosing that we are in the Fermi-Liquid regime, and we can safely use the Fermi-Liquid scaling to extract parameters, including the so-called Maslov criteria on the first Matsubar frequency, that it should be linear in T, and then also looking at the scaling of the scattering rate as well as the spin susceptibility at temperature equals zero, which can be done via NRG calculations. So I won't go into any details of this, but we can have plenty of confidence for the materials that we're looking at that we are in the Fermi-Liquid regime, and we expect Fermi-Liquid scaling. So I mentioned that the accuracy in the low frequency regime of the self-energy was not sufficient in the previous plot. And so one way that we can see this is if we plot, so again, we're plotting imaginary part of self-energy. This is the Pade analytically continued self-energy from the QMC over pi t squared versus omega over t. And we're plotting it versus the eta parameter, which is the parameter of the analytic continuation to omega plus I eta. And what we would expect is if we decrease the eta parameter, we should see some convergence of the analytic continuation. But for strontium vanadate, and we see the same for strontium molybdate, we see that as we decrease eta, we just decrease the self energy or the imaginary part of the self energy at low frequencies. And so if you were to extract a scattering rate from the zero frequency data, then it would depend very sensitively on your eta parameter. And in a material like strontium ruthenate, which has a much higher magnitude of the scattering rate, you don't see this issue. It converges very nicely. It doesn't really matter which eta parameter that you choose. So this is a problem for extracting the scattering rate and therefore the resistivity. But as I said before, we can just use the scaling of in the Fermi-Liquid regime. And we see that out here in the higher frequency, basically frequency greater than the temperature area, we see a relatively robust behavior with eta. And so what we do is we just use the information out here, fit to this Fermi-Liquid scaling, which is this gray bar, to both extract C and also to kind of choose the analytic continuation that gives the correct behavior. So this is the results for strontium vanadate and strontium molybdate. So these plots are a little bit busy, but they're plotting the same thing, imaginary part of the self-energy over pi squared t squared versus omega over t. This is now for different temperatures and including the NRG data, which does not include the analytic continuation. And you can see that the lines approximately collapse onto one curve, as they should for Fermi-Liquid. And we take basically the region of error to be the region spanned by these different curves. And same for strontium molybdate. And so from these calculations, we can robustly extract the C parameter and therefore the T squared parameter of the resistivity from the Fermi-Liquid scattering. Okay, so let's see now. Oh, sorry. One more thing I wanted to say was that I mentioned before this can also be done on the Matsubara frequency. And so Antoine and Fabian came up with this nice little procedure where if we take the same Fermi-Liquid scaling now in terms of Matsubara frequency, we have two unknowns. We have the quasi-particle renormalization and that C parameter. And therefore, we can fit this equation with two Matsubara frequencies. For example, just using the two lowest Matsubara frequencies as we've done here, and get this curly Z and curly C, which can be showed to converge to Z and C as we go to low temperature. And so we've also done this for strontium vanadate and strontium molybdate. So here again are just the self energies, and in the insets, the points are the convergence of C for the orange and Z for the blue as we go down to lower and lower temperatures. And we can see that we start to increase our numerical errors as we decrease temperature, but basically they're still consistent with these blue and orange bars, which correspond to the scattering rates or the Z and the C that we get from the real frequency data. So overall, we have consistency between QMC, between NRG, between real frequency, and between imaginary frequency. And so together, we can have confidence that we have kind of minimized as far as possible our numerical errors. Okay, so that was a lot about the calculation. So let's see how it meets the experiment. So I've now put on these plots of all of these experimental measurements, the DMFT self-energies, or the DMFT resistivities, sorry. And those are these red dashed lines. And as you can see, at first it doesn't look great. They're much lower than the resistivities of the measurements. But if we zoom in to the low resistivity regime and just consider a selection of these measurements that have extremely low residual resistivity, then we see an interesting behavior. So this is accentuated in strontium vanadate and also pointed out in this previous paper, that there's actually two T-squared regimes in this material. There's one that kind of goes up to about 30 degrees Kelvin, and then there's another one for at higher temperature. And our DMFT calculation actually matches fairly well within those error bars that I mentioned, the low T-squared regime. In strontium molybdate, it's a little bit harder to see. The measurements are more challenging in this regime. But you can kind of see that the points are starting to fall below the line and are consistent with our, again, a lower temperature, lower A coefficient T-squared regime. So I think in this Brolick paper, this was called a hidden low temperature Fermi-Liquid T-squared regime, and that is in agreement with our DMFT calculations. So we can, from these calculations, we can attribute this low T squared to electron-electron, Fermi-Liquid electron-electron scattering. But why do we have this high temperature T squared regime? So in the last couple minutes, I'll just quickly go over where this regime comes from with the example of strontium molybdate. And of course, if it's not electron-electron, then the temperature scaling is probably electron-phonon. So with Jenny Coulter, we did electron-phonon calculations. Here are some of the computational parameters. I'll just skip right to the results. So this again is that low residual resistivity strontium molybdate experiment. Here's our DMFT electron-electron calculation. And here is the electron-phonon calculation. And you can see immediately that it not only has this T to the fifth regime that we would expect, but it also has a T squared regime. And when we combine it with the electron-electron, we see that it matches the experiment pretty well. We have a slight overshoot at high temperatures. I can discuss the reasons for that later. But keep in mind that this scale here is in individual microcoulombs per centimeter. So in absolute terms, we're quite close to the experimental results. So why in electron-phonon do we have a T squared regime? So the reason we have a T squared regime, to understand it, we first have to go back to why we expect this T to the fifth regime at low temperature. The reason can be understood if we consider the momentum relaxation time approximation of the resistivity, which includes an electron-phonon coupling matrix element, a phonon distribution function, and a term that selects out the high-angle scattering that actually degrades the resistivity. And these elements have dependencies on, of course, the wave vector of the phonon. And at low temperatures, when we basically have Debye phonons activated, all of the wave vector dependencies of these terms turn into temperature dependencies, because the higher the temperature, the larger the Q phonon we have for scattering. And one of the key dependencies is this phonon distribution function, which basically depends on the intersection between the sphere of radius Q of the phonons available for scattering, the intersection with that and the Fermi surface. And for a small Q and a large Fermi surface, or in any case a spherical Fermi surface, the intersection goes like Q squared. It's a circle. That gives us a T squared. And when we combine it with the other temperature dependencies, we get T to the fifth. And then at high temperatures, we no longer gain more Q by increasing the temperature. We lose a lot of these temperature dependencies and we get T-linear behavior. What we think is going on in these materials is that if you consider a cylindrical Fermi surface and the regime where this phonon Q is large compared to the small axis of the cylinder, but small compared to the large axis of the cylinder, then the intersection between these two shapes just geometrically depends linearly on Q and therefore on T at relatively low temperatures. And we also lose a little bit more temperature dependence. I won't go into the details, but you can show, it was shown in this paper, that gives you a T-squared dependence. And so strontium molybdate and strontium vanadate, they have cylindrical Fermi sheets of their Fermi surface that's been shown with calculation and also with ARPES. And when we use the model of a cylindrical Fermi surface, that is these magenta points here, these orange points here, we see that we can capture this T-squared regime that we see in the full DFT plus Boltzmann transport equation calculation. Whereas what I label as the block model, which assumes a spherical Fermi surface, it can capture the T to the fifth and the T linear, but this regime here is just a crossover between the two. It doesn't have a true T-squared regime. So in this way, with a cylindrical Fermi surface, we really can get a T-squared regime from electron-phonon scattering. Okay, so I think I'm just about out of time. So I hope I showed you some kind of tricks that we use to extract converged Fermi-Liquid resistivities in high conductivity, low scattering rate materials from DMFT using the Fermi-Liquid scaling. And that in these materials, and I think many others, there is a hidden low temperature T-squared regime that actually matches quite well to our DMFT Fermi-Liquid calculations, and a higher temperature T-squared regime, which we attribute to electron-phonon coupling or electron-phonon scattering in a cylindrical Fermi surface. So thanks for your attention. I'm happy to take questions.
Thank you so much, Cyrus, for this very clear talk. And I guess the talk is now open for questions. Lots of applause, not too many questions appearing.
There is one question, Antoine. Yeah.
One question.
Yeah.
Quader, you want to ask a question? You need to unmute yourself.
You're muted. You're muted. Yeah, now it's good.
Good to see you again, Cyrus.
Yeah, good to see you.
I had a question, a comment and a question. So when we did the 112 nicolates, we constructed a phase diagram based upon scattering rates and spin susceptibility, local spin susceptibility. So one aspect we found is a different aspect of T-square behavior. We found an onset T-square, which is pretty high in temperature, which you wouldn't expect. And then it continues down and it almost goes to zero eventually. So we attributed that to the onset. We're not the first one to see such an onset. I think Gabi Kotlier in some other materials had seen a higher temperature onset of T-square behavior. So we attributed to that the d electrons were not being fully screened yet. And then as it goes to lower temperature, they're fully screened. And hence, while the scattering rate shows T-square, it's not a fully screened Fermi-Liquid yet. This is, of course, for d electrons. So that's one question. This is a comment. The question was, do any of these materials show such a high temperature onset, or is it pretty much restricted to the low T square?
So yeah, so I don't think we see the onset that you were referring to, I mean, I guess I would say that we do see two T squared regimes for sure, you know, as you can see in this plot.
Right, but it's
But
different.
the onset is at quite high temperatures, and especially in these materials, which probably have significantly weaker correlations than the 112 nicolates, I would think. And we see a pretty clean Fermi-Liquid behavior from the DMFT, and then I think this transition is clearly at a temperature where, for the level of correlations, phonons should be activated. Of course, we're not taking into account, you know, we have all of the normal approximations that come with single site DMFT, no vertex corrections, static interaction, all of this stuff. And so maybe going beyond that, we will see some different phenomenon. But I think here also there's no indication from the experiment that this phenomenon is seen, or at least it can't be resolved in these cases.
Yeah, I mean, same in our case. It's a no vertex correction, DFT plus DMFT. But the follow-up question was, did you look at the spin susceptibility and see if it correlates at all with the T-square behavior?
Yeah, so we did look at the spin susceptibility. I kind of flashed through that very quickly with NRG. And the Fermi-Liquid, we see basically a nice simple Fermi-Liquid regime in the frequency range that corresponds roughly to the Fermi-Liquid temperature that we see from other indicators like the Maslov criteria and the collapse of M sigma and so on.
Thank you.
Mhm.
Andy's
Thank you very
next.
much. Yeah, Andy.
Hi. All right. I think I unmuted.
No, you're not.
I'm not unmuted?
You are unmuted.
I am unmuted. All right.
You
Excellent.
are.
Okay. I think there were too many negatives. I'm not on. Anyway, sorry. Beautiful talk, Cyrus. So can you go back to your slide which showed the hidden low T squared with the two materials?
Yes.
Yeah, that one. Okay. So for the strontium, I wanted to ask the strontium molybdate, right? We see that the delta rho, which I assume is the resistance measured relative to some low T value, has a slope which is parallel to your DMFT curve, so that the resistivity is T squared within the admittedly large scatter at low temperatures, right? So the offset means that there is some kind of discrepancy between the coefficients, or that we would be seeing a, right. Yeah. So I guess that's right. Does the offset mean that there's a discrepancy with the coefficient? And the reason that I'm asking is that if I look at strontium vanadate, the adjacent one, right, the high temperature resistivity, which comes from phonons, has a different slope.
Yeah.
Right? Whereas the strontium molybdate seems to have the right slope, just an offset. So is it your view that there's some problem with the coefficient of T squared, or do you think something else is going on?
I think from this data, it's just impossible to tell. I think the data in this regime, it depends somewhat sensitively on how you define and subtract the residual resistivity. We discussed a little bit with these authors. I think in general, these are very challenging measurements because the resistivity is so low that you need to apply such a high current to get some kind of voltage. So then you end up potentially heating the sample. So I would say that it's just not well enough resolved to know, you know, if there is some error in our DMFT coming from some fundamental approximations, or if it's experimental uncertainty, or if the slope is far below, or you know, etc. Yeah.
Okay. All right. But again, the striking thing about the comparison of these two pictures is that we see a T squared slope up to quite high temperatures in the data, presumably in the temperature range where the data is good. just with an offset, which is unlike strontium vanadate. So I guess my question was really, how seriously should I take the agreement of slopes with DMFT? And I guess, right, because it looks different from
Yeah,
strontium
yeah. I mean,
vanadate.
I would say in strontium vanadate also the electron-phonon scattering is a lot stronger.
Yeah.
And enhanced by correlations, and therefore it's a little bit kind of a cleaner distinction between the two. Whereas
Mhm.
strontium molybdenate, the reason it has such superlatively low resistivity is because the electron phonon is so low. And
Mhm.
so then the offset between the two, between even
Mhm.
DMFT and what we predict for the electron phonon is somewhat less.
Okay, great. Thank you. So I guess this means that the real answer to my question is this material. It's still the issues are just open. A very brief question in both of these cases. What's the value of the residual resistivity? I mean, are we looking here at resistant delta rhos, which are bigger than the zero temperature?
No, I mean the residual resistivity, yeah, I don't have the actual values,
Okay,
but they're
do.
very low. They're
okay.
in the
So these are all basically, we're talking about basically ranges where it's bigger than the residual.
Yeah.
uh
Yeah.
yeah, tenths of microcoulombs per centimeter in the lowest samples. Yeah. So kind of in this range.
Ah, well, because again, once you get into umklapp scattering and all this kind of thing, there's a big difference as to whether you have impurities around to break momentum conservation. Okay, fine. So let me not take up any more time except to say my favorite word, which is frequency dependence. Are there plans to extend this to look at the frequency dependent conductivity?
Uh, I would say yes. It's an area of active research.
Okay, thanks.
Love that. Yeah.
Right. Great.
If
Thank you.
there, if there are no further comments, maybe I still have, I guess, a minute to make one. As you see, especially from the previous slide that you just showed, Cyrus, yes, this one, the experimental situation, especially for strontium SrVO3, is still very confusing, and especially the single crystal versus thin film situation is confusing. There is even an additional single crystal measurement that is not on this plot, and that adds to the overall scatter. And so if there are experimentalists in the room who would be up to the challenge to trying to clean up that situation, that would be wonderful. That requires excellent samples, obviously.
Yeah. Seconded.